Hi and welcome to this next video from the Forces section from the Year 2 Mechanics course, and what we're doing is building ever increasingly complex models. We've looked at things on slopes, we've looked at forces going in different directions, and now we're going to introduce the idea of friction, and particularly the principle of limiting friction initially, and then also this idea about a coefficient of friction. So let's first of all have a bit of a think about how friction works. And while you listen to the video, it might be a good idea to actually physically do this. So if you just grab yourself a textbook and hold it up in front of you and press your hands either side of the book, so holding it out in front of you with your elbows out straight, and so you've got a force that the force that you're applying with your hands is horizontal. Now that book hopefully at the moment is not moving anywhere, but gravity is acting on the book, so there's a force that's acting in the downward direction, and the fact that it's not moving anywhere means there's also got to be a force acting in the upwards direction. Now, slightly weird because the only force that you're applying at the moment is horizontal, and as we've seen, like kind of horizontal and perpendicular forces don't have any impact on each other, but something's going on here. Now, what it means is it must be that this frictional force here, the thing that's holding the book in place, has got to be coming from the horizontal forces that you're applying to the book. And I mean, it's kind of fairly intuitive and self-obvious, but if you now just start releasing the amount of pressure, so don't push quite so hard the book and release the pressure or reduce the pressure, at some point you're going to get to a point whereby the book will slip out from your hands. So it must be that as you reduce the pressure, the frictional force reduced, and that's what caused the book to fall when the weight of the book overcame the upwards force due to friction. Now, what does all that mean? It says, well, the upwards force must be friction, and which changes as you change the perpendicular, in this case perpendicular meaning the reaction force. So what we've got is a statement there that says friction is proportional to the reaction force, so friction is a function of how much force you're applying horizontally in this particular case. And if you remember back to GCSE, if two quantities as being proportional, you'd write normally kind of if y was proportional to x, you'd be writing y equals kx, where k was just some value. In this particular situation, what we've got is the equivalent, so friction equals mu r. Mu being your constant of proportionality, r is the reaction force, obviously Fr being friction. So that is the big equation that you need to be aware of and you need to know when you're dealing with friction. Right. That one there, as I've said, is the mu is the coefficient of friction. Right. Friction occurs between two rough surfaces and always acts in the direction opposite to the direction of motion. So let's just think about the book for a second again. So we've got this book that's sitting on a horizontal surface, and we haven't got any forces making the book move, so we haven't got any forces applying horizontal to that book, so there's no friction going on, and I'd say no force pushing it. However, as we apply a small force to the book and we try and push it along the desk, it might be that force isn't enough to make the book to move. And so what we must have there is a frictional force that is equal to the force that you're applying. And then if we increase the force that's being applied and the book still doesn't move, then friction must be increasing as well. And that will increase up to a certain point, but it's going to get to a point where the force you're applying is so big that it overcomes the friction and the force moves. So what we've got is this idea of limiting friction, because I said here, until the friction reaches its limit, that's when the book starts to move. So that frictional force is matches the force you're putting into the book up into a certain maximum amount. So we've got the thing moving. And in that particular situation where we've got the book is on the point of moving, where we've applied our force and friction is as big as we can make it, it's in a situation that we refer to as being limiting equilibrium. And the value of that limiting friction depends on two things. Firstly, the normal reaction between the two surfaces, because as we know, friction is proportional to the reaction force. And secondly, the value of mu, which is kind of essentially a measure of how rough or how the two surfaces interact. And what we've done there is just slightly changed our equation from the last slide and said, okay, the maximum amount of friction you can have is mu times r. Right, so that's the idea of limiting friction. That frictional force gets bigger and bigger and bigger until it gets to a point where it can't be any bigger. It's reached its maximum, at which point that's when things will start to happen. Right, That said, let's have a look at an example and let's see what's going on. So we've got an object of mass 5 kilograms pulled along a rough surface by a force of 20 newtons at an angle of 15 degrees to the horizontal. Possibly should have said in the way I set this question up that the surface is horizontal, but it is. Right, so what we've got, let's just chuck our forces on there. So there's our 20 Newton force. We're going to see it accelerating in that direction there. We've got the force due to gravity, the weight. We've got the reaction force. And if we know that the book is going to move in this direction, that means we must have friction going in the opposite direction. Right, let's see how all this is going to work. So let's start off by resolving in the perpendicular direction. So in the perpendicular direction, again, I've said this before in previous videos, that thing is not jumping off the surface. So that means that the vertical forces upwards have got to be equal to the vertical forces downwards. So what we've got going up, we've got R plus the vertical component from this force here. So that's going to be 20 sine 15. And that has got to be equal to the weight, which is 5g. So straight away, we've got the ability to work out the reaction force, which is 5g minus 20 sine 15, which turns out to be 43.8 and a bunch of decimals. Right, now we've got that bit sorted, let's have a look at what's going on horizontally. So horizontally, we've got the force coming from our 20 Newton force, so that's going to be 20 cos 15. And what I'm going to do with this one is that we've got acceleration, that's what we're being asked to find, so I'm going to go for force equals mass times acceleration. So I've got my force here in the positive direction, I've got friction going in the negative direction, the opposite direction to the motion, and that equals mass times acceleration. Now, we clearly, if we're going to work out acceleration, we need to work out friction. So this is where we're going to use friction equals mu times r. And we've got r, that came from our perpendicular force. We've got it from here. So we've got our coefficient of friction times by the 43.8. So we know our frictional force is 10.95 newtons. So now we can just chuck that into the equation there. And so now this is just a value, do the divide by 5, and there we go. Your object is accelerating at 1.67 meters per second. Right, second part of the question. When the object is travelling at 3.5 meters per second, the pulling force is removed. How long does it take for the object to come to a rest? Right, the pulling force is removed. So what we've got is, there's my diagram as it was. Let's remove that force. And so now that's our diagram. Every time we get a change in the forces, I would always advise you redraw your diagram and do all your calculations all over again, because everything is going to change. And we're going to see how things are going to change by looking at our perpendicular forces. Because previously we had our reaction force up here, 5g minus 20 sine 15. Well, that 20 sine 15 has now disappeared, so our reaction force is simply that. And because our reaction force has changed, what that means is our frictional force is going to change as well, from F equals mu r. So let's resolve horizontally, and all we've got now, if we go for force equals mass times acceleration minus friction, it's the only horizontal force we've got, so force equals mass times acceleration, and friction is mu r, so we've got friction is minus 5 over 4 times g, because what I've done there is just gone for, okay, coefficient of friction is 0.25, which is a quarter, so 5g times by a quarter gives us 5 over 4g, and so now we've got that, and therefore my acceleration is going to be minus 1/4 g. Once we've got that, we're saying how long does it take to come to a rest. So the link between F equals ma and suvat is always going to be acceleration. So let's plug in what we know. We haven't got that one. We know it was originally travelling at 3.5 meters per second. It's coming to a rest, so we know v equals 0. We've just got acceleration. We don't care. Oh no, we do care. Time is the thing that we want. Got myself confused for a second there. And so therefore I need the one that doesn't use s, so that's going to be v equals u plus at. Plug in my values, and there we go. It's going to take 10 over 7 seconds, or so that's going to be what's happening, around about 1.4 seconds in order for this object to come to a rest. Okay, now if you remember from a previous video, we had a child on a slope on a sledge being held in place by a horizontal force. So now what we've got, I've removed the fact that on the previous example we said it was a smooth slope. Now we're saying, okay, the slope isn't smooth. We've got a coefficient of friction between the slope and the sled, and again I've gone for a quarter. So how big does the horizontal force need to be in order to move the sled up the slope? So there's my diagram, same as we had before, and if we're going to be moving the sledge up the slope, that means friction is going to be acting down the slope. So it's always important to make sure we've got our friction going in the right direction, because friction always goes against the motion. So let's resolve it perpendicular. So what we've got here is forces going upwards, which is the resultant force, the reaction force. Going downwards, we've got mg cos theta plus x sine alpha. So that's going to be the x sine alpha coming from this one here, and the mg cos alpha coming from weight. That's on that direction there. And now let's have a look at what's going on parallel to the slope. Well, if we assume to begin with, we say, well, let's assume that the forces are balanced, this thing's not moving, it's in equilibrium. So we can say that the forces going up the slope are equal to the forces that are acting down the slope. So what have I got going up the slope? Well, I've got x cos alpha coming from the horizontal force, so it's kind of the horizontal element of this force here. And that's got to be equal to the forces, if it's like say if it's balanced, equal to the forces going down the slope, which is mg sine alpha, which is our weight due to force due to gravity, plus the friction. Now the question says, how big does the horizontal force need to be in order for the sledge to move up the slope? So what I'm going to do is just a little bit of adjustment and say, well, if it's going to move up the slope, I need the force on the left to be bigger than the force on the right. So what I'm going to do is just switch that equal sign out, and I'm going to replace it with a greater than sign, because we need that force there, that x has got to be greater than mg sine alpha plus friction. Okay, so now what we've got to do is get everything in terms of just the one variable. So I need to sort out friction. So let's have a look. Friction, F equals mu r, and r we've got from our perpendicular equation here, and we've got our coefficient of friction, 0.25. But for now, I'm just going to leave it as mu, so we've got that. Sub that thing back into our inequality, and so now we're looking like that. So let's now multiply out this bracket here, and I'm going to do a bit of rearranging as well. So you can see I've multiplied out the bracket, and this mu x sine alpha term is coming from this one over here, which we've just taken over to the other side, because what I'm aiming towards is trying to get my inequality on x is greater than. So x really is the only variable in here at the moment, so I've got it on the left-hand side. Now, you're looking at that thinking, okay, it's not the nicest looking thing, so let's try and make life a little bit easier by slapping in some values. So we know we've got sine alpha is 3/5, cos alpha 4/5, mu equals a quarter. And remember, like this cos alpha value, if you remember from the previous video, we just drew the little 3, 4, 5 triangle, and that's where cos alpha comes from. So let's put those values in. So now it's starting to look a little bit more simple. We can do some tidying up, for example, here. So that's going to be 3/20. So what we've actually got here is 4/5 x minus 3/20 x. And you'll notice on this side here, we've got everything in terms of mg. So all of a sudden, that's now looking a whole lot better. And that clearly the last thing we need to do is to divide by 3/20. And there we go. We end up with our solution. So x has got to be greater than 16/13 mg. And there we go. That's the size of the force that we need in order for the sled to move up the slope. And the last thing I'm going to do with this example, let's say the horizontal force is removed. Let's consider what happens now to the sled as it accelerates down the slope. So, forces have changed, as I've said before, so as soon as your forces change, let's completely redraw the diagram. So what forces have we got going on here? Well, we've got reaction force there, we've got our weight there. Now, the only other force we've got on the slope is friction. The key thing with this is because the sledge is now moving down the slope, that means friction is going to change direction. That's why it's absolutely vital that you redo your diagram and think very carefully about the direction friction is moving in. So, off we go again. Let's do our resolving. So resolving perpendicular to the slope. This one's going to be more straightforward now that that horizontal force has been removed. So the only force we've got perpendicular are r going upwards and mg cos alpha going downwards. And then if we resolve parallel to the slope, let's go for force equals mass times acceleration. So we've got mg sine alpha, which is our force due to gravity, minus the friction, because that's going up the slope. Remember, our sledge is going to move down the slope, equals mass times acceleration, and it's acceleration that we're looking to find. So let's again deal with the friction. So friction equals mu r. Our coefficient of friction hasn't changed. That's still a quarter. Or I'm going to use mu here. So there we go. There it is. So we've got a quarter times by 4/5 mg. Remember, 4/5 being your value for cos alpha. So we've got a value for friction here that's 1/5 mg. And over here, the sine alpha, that's 3/5. So I've got 3/5 mg minus 1/5 mg, and now all of a sudden that's going to look a lot more simple as the m's cancel out. 3/5 minus 1/5, 2/5, so our acceleration is 2/5 of g meters per second squared. The purpose of that question, the key idea there being forces have changed, the direction of motion has changed, so friction has changed direction, so we have to go back to square one, redraw our diagram, redo our calculations, because again with that horizontal force being removed, it's changed the reaction force, which is changing the frictional force, and all new, so start from scratch and away you go. Right, let's have a look at what an exam question might look like. So again, a lot of writing going on in here. So we've got two blocks, A and B, passing over the top of a pulley. We've got the masses of the blocks, we've got the coefficient of friction, and we've got the angle between the slope and the ground. So let's have a go at sorting all this out. So, diagram, let's put the forces on. I've already included those bits there, so that's bit just coming straight from the question. So let's have a look at our forces. We've got the weight on the 5M block, and then we've got tension in the string, so that's the forces acting on that one. What have we got going with the other block? Well, friction is going to be going down the slope, because when the system is released, the 5M block is going to move down, and so therefore tension going that way. And we've got reaction force, and we've got mass. Now, key thing with this one, it says we show that T equals 3 mg. So what we're going to do is we need tension, so we need to treat these two things, because tension is an internal force. We need to treat them as two separate things, get a simultaneous, and then try and isolate T. So here we go. Let's take our 5M block and resolve that in the downward direction, because that's the same direction in which it's going to accelerate. So we've got 5 mg minus T equals 5 ma, using our force equals mass times acceleration. Okay, and then let's have a look at the 3M block. And if we've now got a choice here, we've got two things we can do with it: resolve it perpendicular and parallel. Let's just have a look at what happens if we resolve it perpendicular first of all. So we've got that. R is going to be equal to the force due to gravity going down this line here. The kind of the component of gravity is going in that direction, which is 3 mg cos alpha. And I can tidy that up a little bit, because I can work out the value of cos alpha. Let's come back up here and use our tan alpha is 7 over 24. Same deal again, opposite over adjacent. So that gives us the hypotenuse is 25, which tells us that cos alpha is 24 over 25. So that gives us R is 72 over 25 mg. The 72 comes from 3 times by the 24. So that gives us R. Let's go for resolving that parallel to the slope. So what we've got now is F equals ma, because this thing is moving, it's moving up the slope. So I've got T minus friction minus the component of gravity that's going horizontal to the slope. And again, we can do a bit of substituting here now, because I've got friction coming from F equals mu r. So we've got a value for mu, so let's just plug that in. So that gives us a value for friction. And also I can deal with sine alpha, because coming back to my triangle, you can see up here, sine alpha is going to be 7 over 25. And so we can just plug all of those values in, and so now what we've got is T minus 9 over 5 mg equals 3 ma. Okay, sorted. Now, what we're going to do now is we've got a simultaneous equation. We've got this one here, and we've got this one here, because we've got two variables. We've got T and A are our two variables. A is the one I want to try and eliminate. So what I'm going to do is I'm going to equalise the coefficient. So if I just times that whole equation there by 5 over 3, and the reason I've done that is 3 times by 5 divided by 3 equals 5, and so that will get it the same as that one, and that's what's going to allow me to get those two things to disappear. Again, there are other ways of doing this. If you want to, you could have got rid of the T, worked out A, then gone back and resubbed in to find T, however you choose to deal with simultaneous equations. Okay, I'm going to do it this way. Let's now do a subtraction there. So I've got 5 mg minus 3 mg, so that's going to be 8 mg. And then I've got minus T minus 5 over 3T, so that gives me minus 8 over 3T. That equals 5 ma times minus 5 ma, that's giving me 0. We've got rid of the acceleration like we wanted, and now it's a reasonably straightforward job just to work out the value of T. And there you go. There's the 3 mg that the question was asking for. Okay, so let's move on to the next part. The question says, B reaches the ground, A continues to move up the slope and then comes to rest before reaching the pulley, and then determine if it will remain at rest, carefully justifying your answer. So let's have a look at what's happening now. Well, the first thing to note is that if the string's gone slack, that just takes away the tension in the string, so that force has gone. So let's redraw a diagram and consider what forces do still exist. Well, we've got a reaction force there, we've got our force due to gravity. Now, if this thing here is going to move down the slope, that's the direction of motion, is down the slope, so therefore that means friction is now going to be up the slope. So again, there's a big change because the friction has changed direction. So let's consider what's happening with those forces that still remain. So if we have a look at the forces that are acting down the slope on our block, well, the only force that's going down the slope is the force due to gravity. So that's 3mg sine alpha. And remember, we had sine alpha from before, which was, if I recall correctly, 7 over 25. So that gives us the force down the slope is 21 over 25 mg. The only force going up the slope is friction. So the friction, or the maximum frictional force that we had that from before, was 24 over 25 mg. So that came from the previous question. Because we hadn't got any other forces lifting this block off, that stayed exactly the same. So clearly now we've got a maximum amount of friction, which is 24 over 25. The force down the slope is 21 over 25 mg. So therefore the value of friction is greater than the force down the slope. So A will remain at rest. Okay, last thing, 2 improvements to make to the model to make it more realistic. Standard stuff, any two from, you can use an extensible string, because what happens is there's going to be a certain amount of stretch potentially in any string in real life. And what that would mean is the acceleration wouldn't be the same for both particles. We could include air resistance, we could have friction at the pulley, or just not modelling it as a particle. These things at the bottom, fairly standard stuff. My preference, I tend to go for kind of the extensible string one, because if you've got an extensible string, as I said before, it means that acceleration isn't constant with the two particles, and that basically means that your model just doesn't work anymore. So that would be probably, I think, my personal favourite to go for.